a golf ball, and it's in the grass. You should play in the grass. So we have here the interesting signal. It's the ball. We want to see it. It's in the field. How are we going to see the ball in the field? Well, it depends how high the grass is. If the grass is high, we're not going to see it and we're going to lose it. And if we cut the grass, then we may be able to detect this very small ball. Otherwise, the other way we can, if you want to select to detect the ball in high grass, you need to get a bigger ball. Okay, so this is the signal and this is going to be the background. Now, where is the noise in all this? The noise, the background, is something that does not change from one image to the next. It is real fluorescence, but only it's fluorescence that we don't want, okay? Whereas the noise changes randomly between two consecutive images. And it is not fluorescence, it is something that comes from the imaging process. So we change the readout rate, we're creating noise. This noise is everywhere and it has nothing to do with fluorescence really. So it's not fluorescent, okay? So this is the difference between noise and background. What we call background, very often we just put background, everything is background. We just put it in a big bag, we don't know where it comes from, but we say, well, that's background. So what we call background very often is everything in the image that we wish were not there. For example, the offset of the detectors, we'll talk about all this. Antibody that sticks everywhere, oh, that's background as well. Autofluorescence, this is background. Fluorescence in the mounting medium, all this is background. But really the problem is that if we do not know where the background comes from, we cannot eliminate it. So it's very important to identify what is noise, what is background, what is the source, and how we can deal with it. So that's what we're going to do in this lecture. And you can see this stuff with the ball is that it's either you cut the grass or you get a bigger ball. So if you're stuck with this size of ball when you play golf, you don't want to play with a football, right? So then you must realize that lowering the background and the noise is as powerful as increasing the signal. So when we do not see what we want to see in the image, we have a tendency to want to increase the signal. But very often what we need to do is work on the background and the noise. So cut the grass, please. Here is a nice zebrafish that is autofluorescent, and we're interested in these beautiful cells in here. That's the interesting signal. But look, there is a horrible background around the zebrafish. And then even here, the yolk is very fluorescent. So actually the background can be higher than the noise. The background is the fluorescence that we do not want. So the background can be stronger than the signal. So if we just monitor a little bit, like we make a fake sample, and we can see here the signal is the intensity in the areas we are interested. This is how we can define signal. And the background is the intensities outside the pixels of interest. Okay, so here we were going to have signal, and here we're going to have background. So in these four images, what we have is that we always have the same background. The background is always 100 count, and the signal is increasing. So these are random numbers, so don't quote me on that. It's just for the principle. So here we have a signal that is 150, and therefore we have a signal to background ratio. So we divide the signal by the background. Signal background ratio of 1.5, and then if we increase the signal, we keep the background the same, and so here we have 300, 700, and 5,000. Now we end up with a signal to background ratio of 50. So we have managed to increase the signal to background ratio by increasing the signal, and the background is the same. And you can see that we have a much better contrast in the image. And if you remember, this morning, when we have a better contrast, we can use the full resolution of the system. If we have a low contrast, we are often limited by the contrast, and we cannot use the full resolution. So they talk to each other. So what is a good signal to background ratio? What shall we aim at? The best signal to background ratio is whichever allows you to reliably answer your scientific question. So again, we come down to a well-defined scientific question, and everything is, your scientific question is your guiding star. So it really depends on your scientific question. It depends on what you want to extract from the image the metrics that you want to get. So it depends on the technique that you use to analyze images as well. Some techniques are more robust than others to low contrast. And then what you want is you want to acquire meaningful and reliable data. And that is different from acquiring beautiful images. So meaningful and reliable, this is science. And beautiful images, this is for the poster, for the front page of the journal where you publish. Okay, you also need beautiful images to communicate your science, but the hardcore science where we extract data, it just needs to be meaningful and reliable. So when we want to work on the signal to background ratio, one thing that we would like to do maybe is increase the signal. So how do we increase the signal in the images? So in fixed samples, we don't care too much if the sample there's no phototoxicity. So we can bleach, but no phototoxicity at least. So we can push the illumination power, push these lasers. Some people just stay on 1% all the time. No, we can change. Don't be scared of changing the settings. Push the illumination power, use longer exposure time, maybe slower scan speeds. You can use averaging, we will see that later. And we can bin for a camera. If you use a camera-based system, we can use bigger pixels to collect, to have a brighter image. And then we can have a larger pinhole. So now I'm only talking about how to increase the signal in the images, and I'm not talking about the other disadvantages of, for example, binning, where you lose the digital resolution. But now I'm just talking about how to increase the signal. So we can do that, and the number one is very much how to increase the illumination power. But be very careful when you do a Z-stack, even on fixed samples, you're going to bleach the sample even out of the focal plane, right? Because we're illuminating under and above the focal plane, and so you have to be careful. And you need to be also careful if you need to somehow re-image these samples later. So you might bleach if you do that, if you increase the laser power or scan slowly. If you don't care about bleach, if you don't do a Z-stack, for example, or you don't need to re-image later, just dare bleach every single photon out of your sample to get good data. Think about it. How often do you need to re-image these samples that we keep in the fridge for years? How often do you need to do that? Most of the time, you image it, you get the data, and it's gone, and that's it. And so while you're getting this data, instead of focusing on preserving your sample, make sure that you get excellent data out of it. So dare push the laser. Now, if you have live cells yet, Juan.
I have one comment on that. So I think this is super important because sometimes when you are doing the experiment, this happened to me because I have a paper published from I helped in this paper quite a while ago, and then suddenly there was a question from one other
Reviewer
person, and we had to go back to
and
those
re-image.
slides and then to look for it.
Yeah,
And thankfully, I did not bleach the image, but you at the moment you don't think that you will need it, but you never know, especially when
absolutely.
these results are published,
Yes, yes.
and there might be a need of
Yeah,
re-imaging. Okay, if not you, maybe the other person that is there, or you can, because they will know, they wouldn't know how you did it, and maybe you bleach them and they cannot find it anymore, and it
yeah,
will be more
absolutely. I agree
difficult to
with you.
answer. Yeah.
I agree with you. At the same time, hopefully you have not made just one sample for your whole experiment, and so yeah, then you
Yeah,
have
yeah, yeah. Mhm.
to define your thing. So hopefully, maybe you have several of them, and
Yeah, yeah,
maybe
yeah, yeah, yeah. But
you're
we
imaging
wanted
only part. Yeah,
that exact same place, that exact same slide to answer
exactly.
the question. So
Yeah,
that's the
yeah.
thing.
Yeah, so we have to think about the whole thing in there. But what I see is that many people actually end up acquiring images that are very dim and very noisy. So we'll talk about the noise because they don't dare move the laser power. Some people are being told, don't touch the lasers. So I don't agree with that. I think that we will see why when we look at the noise. But increasing the illumination power is a very, very good way to decrease the noise. It's actually the main way you can decrease the noise. So this is why please do not stay at 1% all the time, and you just dare change this. So you will have to you will have to check, because you will need to go back to your microscope and re-image and try to explore the settings so that you can lower the noise. So we'll see what comes out of that. Yeah, but that's clearly a valid point as well. So if you image live cells, you have to be a lot more gentle with the imaging parameters, and because you want to preserve the biology that you're observing and that you're measuring. This is very important, that the biology that you're measuring is not affected by the imaging process itself. So in that case, you want minimum light exposure. So the minimum required to be able to reliably analyze the images. So there you'd really want crappy images. You want the crappiest images that allow you to reliably analyze the images. What is important here is that you have a low light exposure for live samples. And for all samples, regardless of the are live or fixed, we absolutely want no saturation, no underexposure in the area of interest. That is true for all imaging. And we want to test the whole pipeline from sample preparation all the way to the analysis. So please do not make this mistake of preparing all your samples first, then acquiring all the images, and then thinking about the image analysis. You need to, from the start, go all the way, drive your images to the image analysis. You will learn how to improve the experiment from each step, and then you go back and etc. We have this iterative process. So do not spend a lot of time acquiring a lot of images without testing the analysis pipeline, because the analysis is what drives the experiment. So this was the signal to background ratio, and what we have now, instead of increasing the signal like we have done before, now we're going to change the background. So what we have in here is that we always have the same signal throughout, but then you can see that from here to here, the background is changing. And again, the contrast is decreasing as the signal to background ratio is lower. Or here we have 500, here we have about 2, so we have a lot lower contrast here compared to here. So where does the background come from? How can we influence the background? The background can come from 2 different places. It comes from the imaging condition. It can also come from the sample. So let's have a look at the background that comes from samples. So for example, it can come from the medium. And we already spoke about this several times. It is possible that your mounting medium is fluorescing, or your culture medium is fluorescing. If you have live cells, you have a culture medium, and some of them are quite fluorescent, and this is because they contain flavins and all sorts of stuff that actually fluoresce in green. So for that reason, if you deal with dim fluorescence with live samples, you want to use a special medium that has a low fluorescence. So in here you see, for example, 2 different media, and then we measure in this outside the cells in this region of interest, and we can see here that the mean is 214 in here, and the mean is 101 in here. So much lower in this special medium for imaging. Another source of background, so this was culture medium for live samples, but here we have also the mounting media. It's very common that they age badly, and therefore you need to look at the way you're imaging normally and in the channels that you're using. And you can see in here that we can see this little bubble very, very nicely. So inside the bubble is black, and in the mounting medium we have some counts, and that shows autofluorescence in the mounting medium. So this is why I'm asking you to also do this when you come to us, so that we can just measure and be. But you can also just look outside in the mounting medium where you have no sample. For example, if you have a tissue, just look outside of the tissue. But if you have cells, you need to do this type of controls to make sure. So check this once every few months, let's say, to see how the mounting medium is doing. And if it's like this, just throw it away and buy a new one. So autofluorescence in the tissue, in the culture medium or in the mounting medium are the type of backgrounds that come from the sample. So also autofluorescence, and also immunostaining with a specific binding. So Gabby spoke a lot about this yesterday. Please make your binding stringent so that you do not have a specific binding of your antibodies, and that creates background from the sample. So we have seen this in Gabby's lectures yesterday. Now, background from the imaging conditions, what can that be? One of them can be stray light. So what is stray light? So can you see, I hope that you can see a little something here. Oh, is this specific signal? It's very dim. So very, very dim, a little bit of green signal here. And then if I do this, yeah. What is that? Is this specific or not? Now we see a little bit of green in here, but then suddenly we see tons of stuff. What is that? This is the effect of a desktop lamp pointed towards and away from the microscope with a very sensitive camera on a wide field system. So on the point confocal or on any confocal, it's very unlikely that you will see this effect because we block all the light that comes from the autofocus plane. And this light that we're shining around is really not on the focal plane. So we will block most of this light. But on a wide field system, and especially if you have a sensitive camera, you may see this type of things just from stray light. So it means it's light from the room. Okay. So turn off, if you have such a sensitive camera and a wide field system and you're dealing with very dim fluorescence, you should turn off the overhead lamps when imaging. With a confocal without pinhole, a microscope without pinhole, again, a microscope with pinholes, you don't have that problem because this type of light is rejected by the pinhole. So another type of background that comes from the imaging conditions is the sensor offset. So this is now on the syncopoid confocal. So I remind you that camera-based systems, we have millions of pixels, and detectors on syncopoid confocals, we have only 1 pixel. So this is what we are talking about now, is the syncopoid confocal detectors. And you can change different things in the settings. You can change the gain, and you can also change the offsets. So in some manufacturers have 2 levels of gain, and one of them would be like digital gain, and one amplifies before the electron amplification and the other one after, something like this. But anyway, you can have 2 levels of gain and you also have an offset. So the gain is the how much you amplify the signal that you have. So this is how bright the signal is going to be. And the offset is the sensitivity level. And that is going to regulate all the dim parts in the images. So how low signal you can detect, basically. So we will talk about saturation and underexposure tomorrow, but in all microscopes you are able to, and also in Fiji, you can put the saturation and underexposure mask. So where we can have, and it's sometimes called high-low, where if you have a too high gain, you're going to see things color-coded in red, like here, so it's saturated. And if your offset is too low, you're going to get things color-coded in blue, like this, and that is no good. So we will talk about this later. So if we have a low detector offset, you will get a darker background. But if your offset is too low, then you will get a solid background of a 0 intensity without any nuances. You do not want that, and this type of images are likely to be rejected when you submit to an article, so be very careful because they check this sort of things. Then the detector cannot detect the dim signal. So when we lower the offset very much, you're telling the detector do not detect the dim stuff. Okay, so it's not going to do it. And that cannot be fixed after acquisition because the signal is just not detected. If the offset is too high, what happens is that the background will become a bit gray. That's not a big deal. That can be corrected. So all the dim signals are detected, but this can be fixed later with background subtraction. So if you want to do something with the offset, either you leave it at 0, or if you put it too high, but do not put it too low. So set the offset to the level that is just above the one that gives you blue pixels. So you go down in the offset, and then as soon as you get blue pixel, you go back up until you have no more blue pixels. This is the correct offset level. And whether you're going to have to set the offset or not in your microscope depends on, let's say, how old your system is, because the newer technology normally do not need to set the offset. It is set automatically. So we want to have a black background, not gray, but we do not want to have underexposure. And always keep the saturation and underexposure mask on when you are imaging. So you always have this on, and so you should never see the blue and you should never see the green, and then it means you have the correct settings. And set the detection to get no saturation, no underexposure in the area of interest. And on high D detectors, you will have the offset is automatically set by the electronics. So this is like sort of more modern detectors. You don't need to do that. What happens now on camera-based system? How can we change the background that comes from the imaging condition? We also have an offset in camera-based systems. So now we're talking about camera-based systems with millions of pixels. Sorry, I have the sun in my thing. Do that. Yes. So we now have millions of pixels, and when we acquire an image, we acquire everything at the same time. And if we look in the background in these three color image, so it's three different colors, three different images, we can see that we have a different level of count outside the sample. This is the camera offset plus the background that comes from the sample. Okay, so the camera offset is going to come from the imaging condition, but on top of that, we have mounting medium autofluorescence. So we have two levels, two sources of background in these images. But basically, what is this camera offset? Cameras cannot deal with zero values. The electronic cannot deal with zero values. For that reason, the manufacturers of cameras, they add an offset. So even if you turn off the lasers and you acquire an image, the count inside your image is not going to be zero. So basically, on a camera-based system, you can never undersample because we always start at a certain level. So to remove the camera offset and sample background, all you need to do is do some background subtraction. So what you can do is subtract the minimum intensity of the region outside. So if we select the region outside like this and we look at the minimum intensity, we subtract this value from every single pixel. And we can do this in Fiji in this way. There are different ways, but that's quite easy. So once we have subtracted the background in here, you can see that now we have a better contrast because our images, so the background is very black. So it's also a more pleasing image. So this is after subtraction of the background. So to only remove the camera offset, if we want to keep the background for whatever reason from the imaging condition, but remove the camera offset, then what we need to do is just acquire one image after we turned off the light source. So we turn off the laser, for example, we take one image, and then we look in the whole, all the pixels, and we find the camera offset, which is set by the manufacturer. And this is often 100. On some cameras, it can be 200, but very often it's 100. And you will see that it goes up and down a little bit. So it can be 95 or 105, something like this. But it turns around one value. So if we check everywhere on the image, then we will find the camera offset. This value should be subtracted from the intensity in each pixel in the image. So this is background subtraction that you can do. So let's have a look at why we need to do that. You always need to subtract the background from camera-based images before extracting intensity information from this image. This is especially true if your sample is dim. So let's have a little look. If we have a sample and then we have an area in the sample called A and the intensity is 2000 there, and then we have another area that we're interested in and the intensity is 200. And we know that the camera offset is 100. Can we say that the sample A or the area A is 10 times brighter than the sample B? We can't say that. Because if we do not do background subtraction, so then we are going to say, okay, how much brighter is A compared to B? We're going to divide them and we find 10. Okay, but this is the wrong value because in reality, you need to subtract the background first, and you need to do 2000 minus the camera offset, and then divide by 200 minus the camera offset. And now 19 is the correct value. right? So do not forget, if you extract intensities from an image that is acquired with a camera, you need to remove the camera offset. And again, on a point confocal, you don't need to do that because we have the offset that is close to zero and often set now by the electronics. But on the camera, this is the way it is. So treat all the images in the same way and report background subtraction in your material methods. So this was the interesting signal, and now we've looked at the background, which is very boring. Cut the grass, we can...
Sorry.
Yes.
Can I ask a question?
Please?
Do we have that setting for imaging for the camera-based microscope to check the saturation?
Sorry, I didn't understand.
You have that something to check the saturation and
Yes.
Okay, we have that on camera-based microscope, right?
Absolutely, yeah. Which system do you have?
The Leica
Yeah.
wide field.
Absolutely. So I'm not sure what it's called in the Leica. If anyone knows, does anyone have a Leica system and knows what this saturation mask is called? You will have to find out.
Okay, I can ask
Because
the person.
yes, exactly. And please let me know, because then I know for next time. But basically on the Zeiss system, it's called range indicator. And on the Nikon system, I don't know what it's called. But I think it's called saturation and underexposure. And I don't know about the Leica, but definitely you have that. Yeah. And if you don't, but you do, then you can also look at Fiji. In Fiji, it's called high-low, and I have this information in the in the Fiji instruction document, how to find this. So here we have the signal. Here we have a boring background that we know now how to reduce. And then we have things like this. The grass is not, all the bits of grass are not at the same level. Some of them are higher, some of them are lower, and there's a range basically of grass. And you can see it totally varies which one is long, which one is short. And that is the noise, okay? So now we're going to talk about the noise and see how we can get rid of it. And now we're talking about signal to noise ratio. So this signal to noise and signal to background, they're different. I remind you that the background is real fluorescence, just the stuff that we do not want. Now, to estimate the noise in the image, we do something that you have done this weekend. We take a little time lapse of our sample, very quick, no interval, just quick, 3 little image. And then we play it. And you're going to have to do that to estimate the noise in your images. So this is very, very easy technique. Just take 3 images and then you play the movie. And you can see that the things that change from one image to the next, the things that go wiggly like this is the noise, okay? So the fluorescence, the real fluorescence doesn't change, but the noise changes. The background and the signal are constant. So these are real fluorescence. But the noise is random. The noise is everywhere on the image, regardless of where we are. And it changes from one image to the next because it comes randomly. So if we take 3 images, it's going to be different in 3. It's a bit like snow. So the noise comes everywhere and it comes on top of the signal and the background. And the noise hides dim signals, and that is the problem. If you have a very bright sample, no problem with the noise. If you have a dim sample, that's when you need to really be concerned. So it creates an uncertainty. It's not possible to accurately count the small dots, for example, if we can say, okay, here, where are the small dots? How many do we have? Or it's not possible to accurately measure how big they are because the size and the shape is changing from one image to the next. So what should we consider? So now we re-image this sample with different settings conditions, and I will tell you how to do that. You can see in here in this new little time lapse that it is much easier for us to know. There's still a few changes, but it's much easier for us to know how many dots we have and what shape they have, because we have removed the source of noise. So we have a more reliable image analysis. The data is stronger. So the noise can come from different sources. And once you know when first you differentiate background from noise, then the background, is it from the sample or is it from the imaging condition? And the noise, where does it come from? When you know where all this comes from, you can remove it. So let's see where the sources of noise are. So we have said that we have the quantum efficiency, and so if we have a few photons coming in, maybe not all of them will be detected by the sensor. And then when one is detected, that triggers one electron inside the sensor, and then there's an amplification process, and that leads to an analog signal, which is electricity. So it's a voltage that is read. And after that, we have the analog to digital conversion that gives us one number, and we build one pixel with one intensity number, which is an integer. Here we have a strong source of noise. This is the main source of noise. It's called shot noise. We also have other sources of noise. One of them is called the dark noise. So the shot noise is due to the randomness of light. So it comes from light itself. And dark noise comes from the amplification. So it comes from the machine. And we have other noises that come from the readout. So this process of reading the voltage and converting into a digital system also creates a noise, which is the readout noise. Maybe you recognize this from the speed little lecture. When we want to go faster, we create some readout noise when we change the readout rate. So we have different sources of noise, and therefore we have different solutions. And all this that I'm telling you now is going to be true for all microscopes, so be it detector or camera-based. So let's look at the dark noise first. This is the noise that comes from the amplification of the electrons. It's created by the electronics in the sensor, and it's usually negligible. Now, it depends what you do. If you work with photon countings, then it can be a problem with the electronic noise, but most of the time you can just ignore it. On top of that, there is no setting that you can do to help, because this comes from the detector, the sensors themselves. And so in some cameras, you can buy a cooling system to lower this electronic noise, and that is the very good thing to do. But this is just an extra equipment that you are buying to lower the noise. In general, this dark noise, you can't do anything except change the sensor or add a cooling system. So basically, this dark noise, we're going to ignore it because there's not much we can do. The shot noise now, this is very different. That we can control very much. Light is a random process. So we get these waves, and we have probability to get energy, so photons somewhere. This is the way it works. So it's a probability. So because of that, it's a random process. So there is an inherent noise that is called shot noise, associated with the fact that we're working with light, which is a random process. This is not created, shot noise is not created by the sensor. But it can never be eliminated. So as soon as we detect one photon, we will have some shot noise. It can never be eliminated because of the statistical noise that comes from light. However, the great stuff is that it has it comes like this. So the shot noise, this noise that is created by light, is the square root of the signal. What does that mean? We have in this image, we have less photon, okay? And then we image in different conditions where we get more photons. In this image, let's say we have a very dim signal, and we can say we have a signal of 4, okay? It's just theoretical. So it's here, the brightness in the area that we are measuring is 4. Now the shot noise is going to be a square root of 4, so 2. And therefore, the signal to noise ratio is going to be 4 divided by 2. And that is 50%. 50%, the noise contributes into the image at 50%, which is very high. So the contribution of the noise in this image is 50% if we have a signal of 4. Now we manage to change the conditions in such a way that we get a higher signal. And what happens is that our signal becomes 16. The shot noise now is 4 because it's a square root of the signal. And therefore, the signal to noise ratio is 4, is 16 divided by 4. And now the contribution of the noise in this image is only 25%. So we get an image that is much cleaner because there's less noise in it. And now if we again manage to increase the the signal very much, the contribution of the noise is negligible. It becomes 0.02%. Again, it's a square root. So the higher the signal and the lower the contribution of the noise, even though the noise, as you can see, the noise actually increases, but compared to the signal, it increases very slowly. So this becomes negligible. And this is where we want to be when we image. We want the noise to be negligible for our scientific question. So what does that mean for our scientific question? It depends what we want to measure in this image. If in this image we want to know how many big boulders there are on the beach, no problem, we can see the big boulders even if this extremely noisy image. If we want to measure the length of the shore, we can also do that. And so here we have, we can see the big things, but we have no details here, and we have no details on the beach. But if we look in here, we see not only we see the border, but we see a lot of details in the sky and small bits on the beach. So depending on what you want to measure, this is considered acceptable or not, or this is acceptable. So remember that the shot noise is a square root of the signal, and therefore increasing the signal decreases the proportion of noise in the image. So this means we have a very strong influence on the software settings have a very strong influence on the shot noise. So we have a lot of things to do there when we are at the microscope. How can we decrease the contribution of the shot noise? All we need to do is increase the number of detected photons. And how can we do that? We can increase the illumination power. So push the lasers, the LEDs, the mercury lamp, something. We can increase the exposure time, or we can decrease the scan speed on the point confocal, so we can have longer pixel dwell time. Again, we integrate all the photons going to the sensor. We can open the pinhole if we look at a confocal. And we could also match better the fluorophores and the filter. That will also increase the number of photons that make it to the sensor, and therefore we will have less noisy images. And we can use brighter fluorophores. So clearly this is part of the sample design. And this is true for both detectors and camera. For all systems, you have shot noise as soon as you deal with light, and you can do all these things to decrease the noise, the contribution in the image. So we've seen the dark noise that we can ignore. We've seen the shot noise that we can influence very much. And now we're going to look at the readout noise. And this comes from the electronic noise that comes from the amplification and the reading the voltage. We have a very strong influence there of the software settings. So we can influence this when we sit at the microscope. And the readout noise is linked to the speed of reading, amplifying, and converting all these electrons into a digital image. So the faster you go, the more noise. So how can we decrease the readout noise contribution? We can lower the amplification or the readout rate. So the amplification is going to be the gain, for example. So on single point confocals, if you use a high gain, you're going to have a noisy image. So try to keep the gain at a position where you do not create noise. In that case, you're going to get a dimmer image, but you can compensate this by increasing the illumination power, decreasing the scan speed, so longer pixel dwell time, opening the pinhole, and doing your job when you prepare your sample, okay? So do not push the gain too high because you're creating a noisy image in that case. It is better you have to find the balance between the gain and the illumination power. On camera-based systems, we have spoken already about the speed, so readout rate. By default, use the slower readout rate. So because as long as you don't want to go super fast, you don't need the maximum speed. So use the slow readout. And if you want to go very fast, increase the readout. And then you get, so this is, for example, here we have the readout rate 200 megahertz. So this is what you would use by default is the lower one. And you go up only when you need to. So this was the readout rate. Now, if we have a very dim sample, and we anyway have a high contribution of shot noise in our images, and we cannot immensely increase the laser power, what do? If we have anyway a noisy image, what do we do with it? What we can do is averaging. So what we do with averaging is that we actually acquire several images, and for each pixel, the software is going to sum and calculate the average intensity for each of them and create a new image. Okay, so if we average 2, the noise is reduced by half, but the intensity in the signal or background stays the same. So I said signal and background are real fluorescence, they're always going to be there, but the noise will go down. That's because in here, maybe we'll have, in the first image, let's say if we average 2, in the first image, it's going to be 167 counts, and then the second image is going to be 168 counts. At the end, when in the averaged image, this is going to be pretty much the same intensity. However, in here, we're going to have some noise in the first image and not in the other one. And so the average is going to decrease the noise, but the intensity of the real fluorescence, so background or signal, are going to be the same. Okay, so you do not see this process of acquiring one and the other image. The software will deliver just one image to you, so it's done on the fly. However, the imaging takes double the time if you averaged, so it takes longer. And on top of that, the edges of objects are a little bit fuzzy. And that's because we're removing the noise, but we don't really know where the real edge is. So the segmentation will be slightly less accurate. So averaging is very good as long as you do not need fine segmentation. And also you bleach more because you image double the time. And you have a higher chance for the fluorophores to go to the dark state, especially on single point confocals. So that is, these are the consequences of shining more light on the sample. So how much averaging should we use? You do the same thing to estimate the noise. So you acquire a 3-image time-lapse without averaging to estimate the percentage of noise. Then you see your little time lapse. I think these are not time lapse. So if you look at the little time lapse that is playing and you go like, okay, does the noise prevent me from reliably answering my scientific question? If it does, so have you tried reducing the shot noise by increasing the illumination? Have you tried changing the readout noise? If you have already done these solutions, then maybe you need to use an averaging tool. As long as it prevents you, the noise prevents you from reliably answering your scientific question, and you have already tried the other solutions, then you average to and you test again. This is the way you do. By default, no average, and then if it's a problem, you can average. Okay, and you test every time, and the minimum averaging is the correct one you want. And so this is true also for detectors and cameras. So now I look at where I am. All right. So, okay, I will just want to quickly have a look. Oh, I'm almost finished. Okay, great. Click. Oh, not what I wanted to do. I want this one here. Okay, so the contrast, signal to noise and signal to background ratio. We have seen that we have the signal is the intensity in the pixels of interest. The background is the intensity outside of the pixel of interest. It's something we do not want, but that's where it is. And the noise is a random variation of intensity from one pixel to for one pixel from one image to the next. So in the single pixel from one image to the next, we're going to have a variability, and this is the noise. The same signal here at the center, we have the same signal of 300 everywhere, and then we have some background, but we have different noise. So the background is not going to change in here, but the noise is going to change. And what you can see is that as the signal to noise ratio decreases, it starts here at 100 and it becomes pretty bad with high noise. So it's very difficult for us to identify where this signal is. Whereas in here, with a high signal to noise ratio, we could easily identify the signal. So what is a good enough signal to noise and signal to background ratio? Whichever allows you to reliably answer your scientific questions. So these are the things that only you can answer based on your scientific question and how much the background and the noise bother you. So here are the conclusions for this lecture. The background and signal are located at stable places in the sample and they are real fluorescence, whereas the noise appears at small dots, like pixel size dots, that appear at random locations between and are different between images. This is not real fluorescence. It comes from the way we acquire images. Increasing the signal is a very efficient way to improve the image. So make sure that you don't get tricked by pushing the brightness and contrast. And when you set your settings on the microscope, you think that the image is bright just because you're pushing the brightness. No, make sure that you explore the image, and you should not have a too dim image. Otherwise, if the signal is too dim, you're going to have a high contribution of the noise. Decreasing the background and the noise is a very efficient way to improve an image. It is as efficient as increasing the signal. So you can work on both ways, increase the signal, but also decrease the background and the noise. The signal to noise ratio is often wrongly used for both signal to noise and signal to background ratio. This is a very common mistake. So now you know that the noise and the background are different. They have different possible sources and therefore different solutions. And the background can come from the sample or can come from the imaging conditions. And mostly it comes from the sample or the camera detector offset. It depends how bright your sample is. And the noise is mostly shot noise and also readout noise. But if you use the default minimum readout noise, then what you're seeing in the image is shot noise. To decrease shot noise, increase the signal. So you need to increase the number of photons that are detected by the sensor. Therefore, you need to choose fluorophores that work for your microscope. And then on the excitation and the emission side, you need to increase the illumination power or increase the exposure time or the pixel dwell time. And to reduce the readout noise, all you need to do is reduce the gain on the detector or reduce the readout rate on the camera-based system. And then you have to compensate by increasing, for example, the illumination power. Averaging and post-acquisition processings are very efficient ways to remove noise as well. So there are denoising algorithms as well that you can use after acquisition. You need to think, what is your goal when you acquire this particular image just before you click on the acquire button? What is your goal with this image? If you're looking at acquiring a big overview of the sample, you don't care about the noise. It doesn't matter if the sample is noisy. If all you want to see is for example, the edge of a region of interest, you just want to find the region of interest, then clearly a noisy image is going to be fine. And therefore you're okay with lots of noise. And then when you want to acquire the images where you're going to extract the data, you ask yourself the same thing. So it's really important that you try to estimate the noise and background and try to see, are they preventing me from answering my scientific question? And if you want to publish an image in the front page of your favorite journal, make sure that you acquire a beautiful image, very bright, with no noise. And there you just bleach the thing to death. It's okay. And to get data for analysis, however, try to acquire an image that allows you to reliably answer your scientific question. Just focus on that. Do not believe your eyes, okay? So now I am finished in here and I want to know if there are any questions about this part. No? Okay. But then you will have to now, after this, you will have to estimate the signal to noise and signal